Hey guys, so today we're going to start talking about imaginary numbers. I know that sounds funny, what is an imaginary number? But trust me, they exist. So the square root of -1 has no real solutions. So to solve the solution, the imaginary number I was invented. So that's all it is. Imaginary numbers are the square root of -1. So here we have I squared. I squared is -1. Because I is the square root of -1. Normally, we can't have the square root of a negative number because there are no real numbers that when multiplied by themselves give you a negative. For example, -2 times -2 is +4. +2 times +2 is also +4. So there's no way to multiply a number by itself to get a negative number. But we needed one, so we invented I. So how do you write an imaginary number? Well, an imaginary number is any number that can be written in the form I, where A is any real number at all. We simplify imaginary numbers the same way we simplified other radicals. So for example, here we have the square root of -5. We can simplify -5 to -1 times 5. And we now know that the square root of -1 is I. So if we pull out the square root of -1, we get I square root of 5. Okay, now we also have here the square root of -36. So let's go ahead and break that down. -36 is -1 times 6 times 6. And so we're going to pull out our 6 because there's a pair. And we're going to pull out our -1 because that can go to I. So the square root of -36 is 6I. Here we have the square root, 3 times the square root of -50. So we're going to have 3 square root -1 times 25 times 2. And 25 is a perfect square, so we're going to pull out its square root, which is 5. So we're going to have our 3. We're going to put a 5. And -1, the square root of -1, is I. And so what we have left as our surd is just 2. Now we still have to multiply what's on the outside. So we have 5 times 3, which is 15. I always goes at the end, times the square root of 2. And that's all there is to that. Simplifying is just like simplifying radicals, except now you have negative numbers. Now the operations with imaginary numbers are very, very similar to when we combine like terms. You can only combine imaginary numbers if they are both imaginary for addition and subtraction. For multiplication and division, we can do pretty much the same thing we always do. We have 3 times 2 is 6. I times I is I squared. Now I squared is -1. So that would be 6 times -1. And that gives us -6. So when we multiplied I times I and got I squared, that's the same as when we multiply x times x and get x squared. Now, if we're going to multiply a real number times an imaginary number, we're going to do it just the way we've done regular numbers. So, for example, if we had 3 times 4x, that gives us 12x. Same thing you can see here. 10 times 3i gives us 30i. Okay, so now how about if we divide two imaginary numbers? We have 3i over 4i. So 3 over 4 does not simplify. We're just going to keep it as 3 over 4. And I divided by I. Anything divided by itself is 1, so we don't need to write anything. 3i over 4i is 3 over 4, just like when 3x over 4x is 3 over 4. Now, when we're dividing an imaginary number and a real number, it's again the same as when we are dividing regular numbers. So we have 5i over 7 is equal to 5 over 7 times I. We get the same thing if we were to take 2x over 3. We would simplify that to simply 2/3 x. It's not much different than working with real numbers, just a little bit. So what about other operations? Now, we've seen radicals simple like the ones you see in front of you, the square root of negative 16 minus the square root of negative 49, I square root of 2 plus 5i square root of 2. But some operations do not work the same way with imaginary numbers. Now, with addition and subtraction, they do still work. You can combine them if they're like terms. You can't combine them if they're not. However, with multiplication and division, it doesn't work the same way as when we were multiplying radicals. When we multiplied radicals, if we had the square root of a times the square root of b, we would end up with the square root of a times b. But when we're working with imaginary numbers with the negative square roots, that does not apply. The same thing as when we were dividing radicals. We'd have the square root of a over the square root of b is equal to the square root of a divided by b. But again, with imaginary numbers, that is not the case. You have to simplify first. So let's look at example D. Example D has the square root of negative 16 minus the square root of negative 49. So what we're going to do is we're going to simplify the square root of negative 16, and that's going to become 4i, because the square root of 16 is 4, and the square root of negative 1 is I. And we are going to subtract the square root of negative 49, which is 7i. 4i minus 7i gives us negative 3i. Just like if we were combining like terms. Remember, we can only combine them if they match. Again, with e, we have I times the square root of 2 plus 5i times the square root of 2. And the same rules apply as when we were adding radicals. If the radicals match, we can add them. If they don't, we cannot. So we have 1i times the square root of 2 plus 5i times the square root of 2 is going to give us 6i times the square root of 2. That's pretty simple. But look at f. We have the square root of negative 4 times the square root of negative 25. If we were to multiply negative 4 times negative 25, we would get 100. And the square root of 100 is simply 10. But again, like I said, it doesn't work that way with the negatives. We have to simplify first. So the square root of negative 4 is 2i, and the square root of negative 25 is 5i, which allows us to go ahead and multiply these two together, and we get 10i. Okay, so that's the same thing, same process, but with the i's, we have to do it a little bit differently. Now, finally, we have g, which has 21i over negative 7. We do the same thing we would in any regular real number problem. 21 divided by negative 7 is negative 3, and I just stays because I divided by 1 is I. Now, closure here. Now, we haven't discussed closure much. What closure means is that when you perform an operation, you get the same type of number. So in this case, we have it closed under addition and subtraction. And what that means, if you look above, when we added and subtracted, we still ended up with the same type of number. We had i's. When we have 4i minus 7i, we ended up with negative 3i. That's the same type of number. When we had f with multiplication, it didn't work exactly the same way we normally would. We ended up with an I number instead of a square root. So it's not closed under multiplication and division. Division. Okay? We can divide and multiply imaginary numbers and get real numbers, but we can't add and subtract imaginary numbers and get real numbers. It's the same set. So what do we do when we're multiplying I by various powers? Well, I to the first is I. Anything to the first power is itself. We already know that I squared is negative 1. So if we have I to the third, we have I squared, which is negative 1, times I. So that gives us I times negative 1, which gives us negative I. If we have I to the fourth, we have I squared times I squared. That's negative 1 times negative 1, which gives us positive 1. Over here we have I to the fifth. I to the fourth times I gives us 1. Because I to the fourth is 1 times I just gives us I. We have I to the sixth, which is I to the fifth times I. I to the fifth is I. I times I is I squared, which is negative 1. I to the seventh is I to the sixth times I. We've discovered that I to the sixth is simply negative 1. Negative 1 times I is negative I. I to the eighth is I to the seventh times I to the first. I to the seventh, we already determined was negative I. And negative I times I is negative I squared. Negative I squared is 1 because I squared is negative 1. Negative times negative is a positive. So we can see here there's a repeating pattern. I, negative 1, negative I, positive 1. I, negative 1, negative I, positive 1. So what you're going to do is divide the exponent by 4. If it divides evenly, the answer is 1. 4 divided by 4 is 1. 8 divided by 4 is 2. And in both of those cases, we ended up with 1. If it has a remainder of 1, the answer is I. So let's look at I to the fifth. 5 divided by 4 is 1 remainder of 1. We got I. If it has a remainder of 2, the answer is negative 1. I to the sixth divided by 4 is 1 remainder 2, and we ended up with negative 1. And same thing with the remainder of 3. I to the seventh, 7 divided by 4 is 1 remainder 3, and we got negative I. The pattern will always work. So let's give it a try and see how it works. We have I to the 15th. I to the 15th is going to be I to the 12th times I to the third. And 3 is our remainder. If we took 15 divided by 4, we would get 3 remainder 3. So because we have a remainder of 3, it's going to be negative I. For the next example, we have negative I to the 16th. So that's the same thing as negative 1 times I to the 16 divided by 4. And 16 divided by 4 is 4. There's no remainder. No remainder. And what that tells us is that the answer is going to be 1 for what's in the parentheses. Now we do have to multiply that by negative 1 because we had a negative 1 in the original problem. So how do we rationalize an imaginary denominator? Remember when we were doing radicals, we had to rationalize the denominator. We can't leave a radical in the denominator. And it's the same thing with the imaginary numbers simply because I is the square root of negative 1. So let's take a look at this example. 3 over 4i to the 7th. I to the 7th is negative I, so we're going to simplify this. We're going to have 3 over 4 times negative I. So how do I get rid of the negative I? Well, the negative can just be put in front of the 4. That's perfectly fine. And we're going to get rid of the I the exact same way we got rid of radicals. Now remember, if we're going to multiply the denominator by something to get rid of the radical, in this case the imaginary number, we also have to multiply the top by that because in order to keep it equivalent, we have to multiply it by some variation of 1. So I divided by I is 1. So that gives us 3i, because 3 times I is 3i, and we're going to have negative 4 times I squared. I squared is negative 1, so let's rewrite that, 3i over negative 4 times negative 1. Negative 4 times negative 1 is simply 4. So we're going to have 3i over 4. Or you can write it as we showed earlier, 3 over 4 times I. It's the same thing as when we wrote with regular real numbers and variables. So let's go ahead and go through a few more examples. Number 1, we have the square root of negative 81. So that's the same thing as square root of negative 1 times the square root of 81. Square root of 81 is 9. Square root of negative 1 is I, 9I. For number 2, we have negative 4 times the square root of negative 36. So negative 4 stays on the outside. Negative 1 times 36. Square root of 36 is 6. And the square root of negative 1 is I. And that gives us nothing under the radical, so we've gotten rid of everything in there. 6 times negative 4 is negative 24 times I. Okay, so now we have 5I times 3I. So we're basically going to split this into two parts. We have 5 times 3, and we have I times I. That gives us 15 times I squared. I squared is negative 1. So our final answer is going to be negative 15 because 15 times negative 1 is negative 15. Now, in the calculators, we can use the imaginary numbers. So if you want to look for an imaginary number on your calculator, you put in your regular number, and then you hit your pi button, and you select the I times 3. Pi button, I. You can check your work, negative 15. All right, so the next problem we have here is the square root of 7 times the square root of negative 7. So we need to simplify first. So that's going to have the square root of 7 times the square root of negative 1 times 7. Now we can go ahead and bring that negative 1 out. The square root of negative 1 is I, so we're going to have 7 times the square, I times the square root of 7. And we can still do that. That's going to give us I times the square root of 7 times the square root of 7. And the square of anything under a radical, the square root of 7 times the square root of 7, is just 7. So this is going to give us 7I. And because imaginary numbers are simply numbers, we can go ahead and use our calculators with them. We can do the same thing for number 5. We have the square root of negative 3 times the square root of 6. So we're going to go ahead and bring the I out first. I square root of 3 times I square root of 6. And then that is going to give us I times I, which is I squared, and then times the square root of 3 times 6. That's going to give us negative 1, because I squared is negative 1, times the square root of 18. 18 is 9 times 2. Square root of 9 is 3. So we're going to have negative 1 times 3 times the square root of 2. And we're left with negative 3 times the square root of 2. Easy peasy, lemon squeezy. No big deal. So let's look at number 6. Number 6 has the square root of negative 3 plus the square root of negative 27. So we are going to have to simplify those. So we're going to have I times the square root of 3. And then 27 is the square root of negative 1 times 9 times 3. 9 can come out, so it's going to give us the square root of 9, which is 3, square root of negative 1, which is I, and then that's going to give us times the square root of 3. 1I plus 3I is 4I times the square root of 3. I'm going to rewrite that because it looks ugly. 4I square root of 3. Number 7, we have I times the square root of 18 plus the square root of negative 8. So this one's going to be a little bit different. We have to simplify it first, just like every other time. So I times the square root of 18. So let's see what that gives us. 18, pretty sure we did that one. If you look over at number 5, we discovered that the square root of 18 is 3 square root of 2. So we're going to have 3i square root of 2. And 8 simplifies to negative 1 times 4 times 2. So we're going to have plus 2, because that's the square root of 4, plus times I, which is the square root of negative 1, and our surd is 2. So now we have 3i plus 2i, and that's going to give us 5i times the square root of 2. Number 8, we have 3 square root of 2 minus the square root of negative 50. Again, we have to simplify first. So the first one, 3 times the square root of negative 2, is 3i square root of 2. And we're going to subtract. 50, negative 50 is negative 1 times 25 times 2. And we're going to do the same thing we did in number 7. We're going to take out the square root of negative 1, which is I. We've got the square root of 25, which is 5. And our surd is 2. So 3i minus 5i times is going to be negative 2i, and it's times the square root of 2 because we're treating them like terms. Now, we have the negative I squared. So that is the same thing as saying negative I times negative I. And that is going to be, sorry, you can't really tell the difference between my negative and my times sign there. Negative I times negative I, and that gives us I squared. I squared is negative 1. So those are just some examples of what to do with imaginary numbers. Yes, it does get more complicated. Eventually, we start adding real numbers and imaginary numbers together into a binomial, and that gives us a complex number, but that's a video for another day. If you have any questions, feel free to leave them in the comments down below. And if you want to be notified when I bother to upload a new video, feel free to subscribe. Bye, guys.